All right, everyone. So next we have Wiktor Kaluza talking about an introduction to malware. Thank you very much.
Working? There we go. All right. So hello, everyone. My name is Wiktor, and today we'll be talking a little bit about malware. So we'll be covering like what malware is, what malware isn't, and kind of try to develop your understanding of why people actually bother to, write malware, why we analyze it, and all the kind of quirks that come with it. And in the latter half of the presentation, I will delve into a case study of a sample that I reverse engineered to give you a taste of what reverse engineering is like, what it is, and what kind of things malware authors get up to. So, before we begin to get into the meat of the topic, I guess you should know a little bit about myself. I'm a mathematics student here at the university. I've been reverse engineering for the past, I think, 5-6 years, if not longer. And I've been professional software that I just found online, just for the fun of it. I also have quite a bit of professional experience I just found online, just for the fun of it. I also have quite a bit of professional experience in the field. So I've interned at places like F-Secure Labs. I've interned at the university here, and I've also done quite a bit of freelance work, all of which were related to malware, where I reverse engineered various samples and kind of developed my skill set over there. The last thing I would like to mention is that I am the current vice president of SIGINT, so if you find this talk interesting, or if you have a general knack or interest in cybersecurity, we're a bunch of quite enthusiastic people about the things that we do, and we'd love to have more of you on board to embrace the journey that cybersecurity is. All right, so now that I am a little bit warmed up, it is time to warm you up. So before we can kind of delve into, talking about malware properly, we kind of have to define what it is. So does anyone have any idea what we would define malware as? Anyone? Yeah, you in the back?
We consider malware as software that is designed with malicious intent to vulnerate an attribute or to destroy another person's computer.
Yeah, that's a pretty good definition. So if someone didn't hear what they said, it's basically software that is with malicious intent to, with the purpose of destroying perhaps your computer or doing bad things that you don't want to be happening to your PC. So another definition that I've kind of come up with, which is quite broad and vague, is code that you're running on your computer that you do not want to be running. And as you can imagine, this is quite vague, quite broad. We can include things like Windows under this. I'm very happy that people found this funny just as much as I did when I was making this presentation. But so this is this could encompass malware, at least intuitively how we view it. Another definition that I found online was from Cambridge Dictionary, which says something along the lines of the person in the back. Software designed to damage the information of other people's computers and prevent the computers from working normally. Now, we might ask ourselves, what does it mean for a computer to not work normally? You could be running malware and it still works the same way. The point of this exercise is that this is all context dependent. It's very difficult to define specifically what malware is, but in general, people have a kind of intuitive understanding. And I think we'll stick to the idea of software that is intentionally or sometimes unintentionally kind of bad and attempts to cause damage to you, your computer, or networks in your organization. So, kind of having an understanding for what malware is, we might want to ask ourselves what malware isn't. And in the same way, this is quite a difficult concept to define. But I would like to kind of bring the idea of intention into the entire spectrum of this. So how many of you know what TeamViewer is? Raise your hand. Yeah, that's about most of the room. So for those few of you who don't know what it is, it's effectively just software that you can install on two computers. Someone gives you a code, and they get remote access to your computer. They can view your desktop, control your mouse, your keyboard, your everything. And this is usually used in like an IT support scenario. You work at a company, your IT support team is somewhere remote, they need to access your computer, that's how they do it. And so, there's nothing malicious there, you voluntarily give access to your computer. On the other side of the spectrum, we have things like remote administration tools in general, more in the context of malicious software, where a malicious actor might want to install such a tool on your computer and, perform things that you don't want them to be doing. So they might be recording your screen, they might be controlling your mouse, and, the intention here is that they are doing this in order to, steal your information or do something that we would consider to be harmful. So there's a significant kind of difference in the intention of those tools, even though that they are quite similar. Malicious actors could use TeamViewer for malicious operations, but usually, that's not the case, and quite a lot of the time this doesn't happen. So kind of keeping the idea of intention into the spectrum of our definition, I think is a good way to approaching what malware is and what it isn't. So we can kind of, perhaps define malware software that is not malware as software that attempts to do what it's advertised to do within some sort of reasonable boundaries and with no ill intent. To further kind of elaborate on that, I kind of threw you into the abstract here, defining software. And I think the best way to approach it, we'll wait for that. The best way to approach, I think, malware is kind of looking at also the aspect of functionality. In today's world, a lot of malware has labels. We have things like ransomware, we have banking trojans, we have cryptocurrency miners, we have botnets, et cetera, et cetera. And new types of malware are constantly being labeled every single day. As technology progresses, we have things like new IoT devices. IoT malware is becoming a thing. These labels develop as technology kind of develops. So we see that these things are usually categorized by functionality, which is another important aspect into considering what malware is. Companies go out of their way to label specific kinds of malware as something because they do very specific operations on your computer that fall under a specific category. So kind of to delve into more specifics, for example, ransomware is just software that encrypts the files on your disk and demands you to pay them money in order to get your files back. We have things like remote administration tools, which I've talked about recently, right? It's just the idea of taking control over someone's computer using software. We have botnets, and these are just large networks where some malicious actors has infected like millions of computers, for example, and they can control each and single one of them and use them to do things like spam campaigns or perhaps distributed denial of service attacks. So it's like a huge network of computers that is connected into like one kind of central authority who the malicious actor would be. We also have things like worms. So what those are is just simply put malware or software that tries to spread as much as possible. So you put it on one computer and one of its primary goals is to simply spread as much as possible over a network, if not further. And a lot of these kind of labels, they intersect quite a bit. No malware is necessarily strictly of one type, and that makes kind of the classification of malware a bit difficult. But people are clever, and they've come up with schemes to place more importance on specific types of functionality depending on what kind of malware we're looking at. So some sample could be a banking trojan and have some sort of ransomware functionality. So you have to make a decision as to, is it a banking trojan or is it ransomware? And people, have this developed kind of schemes at companies to help us doing that. So another aspect to kind of bring into this is that we can kind of understand what malware is just by looking at the specific functionality that it performs on your computer, and usually that is, with malicious intent. So to give you a bit more kind of insight into what these things are, we can consider 3 examples. So in the case of ransomware, back in 2017, we had something called WannaCry. I'm sure many of you have heard of this, but it affected the NHS in the UK and stopped their operations. People who were supposed to get help were unable to get help because the healthcare system was infected and not operating properly, and that's a big deal. A famous example of a worm is Stuxnet. Initially, it was developed to, I think, attack Iranian nuclear facilities. But in the process, it kind of developed into something much more, and people kind of changed it to attack things like water treatment plants or certain parts of the energy industry. And a third example could be the banking trojan that we'll be looking at a bit later in the presentation, Dridex. And what this does is simply that it infects your computer. It tries to extract lots of different credential information for your banking and tries to execute fraudulent transactions on your behalf, effectively stealing your money. So, now that we hopefully have a little bit of an understanding for what malware is, we might want to ask ourselves, why do we care? Why do people write malware? Why do we analyze it? Have the intentions of malicious actors or people who write malware changed over the years? And the answer is yes, it has changed quite a bit. So I would like to take you on a small history tour of what malware was in the past and develop it into what it is today. So going all the way back into the 1960s, the first computers are coming about, and people don't necessarily have a strict idea of malicious software. Some people, like even John von Neumann himself, had some ideas like, oh, what if we had self-replicating software on computers? But these were just ideas. And of course, people like ideas and they like putting them into practice. So around the 1960s, people started being like, oh, what if we had actual software that goes and spreads and replicates? And so it went into that development cycle. I would like to call this the malware revolution, where malware started kind of being created. So fast forward to the 1970s, we see more and more malicious software kind of coming about. A famous example is this guy here. He looks cute on the outside, but is actually quite sinister on the inside. You should be scared of him. And this malware was labeled Rabbit simply because when it infected your computer, it multiplied on your computer to the point of overloading and crashing it. Going further into the 1980s, we have things like Elk Cloner. This software infected floppy disks, and whenever you inserted a floppy disk into an Apple computer, it kind of infected your disk, any subsequent floppy disks that you also inserted, and all it did was really to display a poem on your computer, which was titled "The Program with a Personality." So people were like, well, this is harmless, this is very funny, so why not give infected floppy disks to our friends? So people just shared malicious software in jest to have fun with their friends. No harm was made. It was just really kind of hilarious. Now, fast forward to 1988. I think one of the most kind of historical landmarks of malware. We have Robert Morris. He was an undergrad, I think, at Cornell University, and he wanted to gauge the size of the internet. And there's no better way to do that than to create a computer worm that spreads basically everywhere on the internet, because that will give you an idea of how big it is. So he didn't originally intend to implement any malicious functionality, but unfortunately his code has bugs. And those bugs caused quite a lot of damage. So he launched his campaign. He was like, oh, I'm going to find out how big the internet is. Unfortunately, he ended up infecting NASA and I think putting their systems to a standstill, which they were not very happy about. And they wanted to persecute him for it. He actually managed to remain anonymous for most of the time until his dad convinced him to kind of plead guilty, and he didn't get too harsh of a sentence. In fact, you can see the floppy disk with the original source code in one of the museums. And I think he was also the first person to actually be convicted of such a crime. It was quite recently after there was, I think, Computer Fraud Act that was passed in the US. So historically, the first person to be convicted for malware is Robert Morris. Going further into the 1990s, people start, developing malware. They start having a bit of different intentions now. A bit more vandalism is happening. So we have the Michelangelo virus. What does it do? Well, on the 6th of March, it would erase your hard disk. And why the 6th of March, you ask? Well, because that's the birthday of this Renaissance painter called Michelangelo. And you know, they caused like a very big media outbreak saying like, oh, you know, we've infected millions of computers, and people were panicking. In reality, it was about like 10,000 computers, so they didn't actually do that much damage. But we should probably still feel bad for those 10,000 that lost their hard drives that day. You know, so malware kind of develops in this kind of more malicious intention, with those malicious intentions, and we go into the 2000s where we have the I love you virus. All this does is simply, you know, you receive an email with an attachment. It's supposedly a love letter from your secret lover, and you know, people are dumb, so they click that attachment, and that attachment executes some code. It does, you know, it steals your Outlook address book and then sends itself to everyone in your address book. So that's the way it was spreading. Then it does some funny stuff to your computer that you might not enjoy. And in fact, I think this virus infected like the government, the parliament, the Pentagon even. So it caused a lot of damage. I think shut some mail servers down and things like that. So it was quite a big deal at the time. And now the last thing I would talk about is, I think, perhaps something you wouldn't expect or see in this presentation. I would like to talk about Sony. So Sony decided that we don't like piracy, and fair enough. So they decided to infect their CDs with a rootkit. That rootkit infected the operating system. It changed certain parts of its functionality to make it hard to remove, and in order to monitor the system for any kind of piracy behavior. Unfortunately, this introduced a lot of vulnerabilities into the system. And malware authors were like, a lot of people get Sony CDs. It's vulnerable. You know, what do we do with that? Well, we abuse it. So Sony got into quite a bit of trouble for introducing these kinds of vulnerabilities into your systems, and people weren't happy about it. So, you know, fast forward to today, malware has grown into a much more complex manner, as we'll see a little bit later. But what we can kind of draw out of this history lesson is that they were kind of three primary motivations for why people were writing malware. And that was fun, curiosity, and vandalism. You know, people wanted to mess with their friends. You know, why would you not write malware that, you know, has a funny poem on someone's computer? Or pops up some kind of old school GIF that has some sort of thing playing around it. Of course, people are also curious, like in the case of Robert Morris, you know, gauge the size of the internet. Some people might be more curious on the side of like, oh, can we break systems, you know? There's a lot of technological kind of development that you can do here, and it's all pretty cool. And in the end, we also had vandalism, you know, people that just want to see the world burn, and so they write malware. Now, this has changed a little bit over the years, and I would say that we have around 4 kind of main categories and motivations for why people write malware today. Does anyone have any idea what some of those could be? Ennis? Yep, financial motivations, that's one. Does anyone have any ideas for any other one? Yeah? Yep, political motivations, great. You're basically doing the presentation for me right now, you know? But yeah, like there's 2 other ones that I would like to mention, and that's hacktivism and always fun. So, you know, money, obviously, people make lots of money off malware. Political motivation, nation states, big deal. They want to spy on someone. Malware is a good way to do it. They want to meddle with some country's political business. Malware is also a good way to do that. Hacktivism, you know, people have political motivations and political agendas that they would like to push forward. Malware is also a way to do that. And in the end, people also like to have fun and they're curious. And some people develop malware not to spread it, but just to kind of investigate its technological kind of complexity. So from this, we can kind of develop the idea of 4 types of threat actors, so to say. So there's financially motivated threat actors, there's politically motivated threat actors, you know, there's also the hacktivists, and we have just people doing things for fun. And I would like to talk a little bit about the financial motivations, because, you know, malware is big business, and I mean huge. Like, this is a multi-billion-dollar industry. You can probably make a living off like selling malware or writing malware, and you know, as long as you don't get caught, you're pretty much fine. And you know, you've heard of things like infrastructure as a service. You've heard of the cloud like AWS, Azure. the malware authors were like, well, we're going to have that too. So they were like, yeah, ransomware as a service, great idea. Malware as a service in general, superb idea. So, they went out like, I will write this malware and I'll give it modules. Like, you can have like a credential stealing module, you can have a keylogger, something else. People can tick those boxes on darknet markets, pay the price, and there you go. They get their malware that they can send to some people. And this has become quite a bit cooperative, almost as like big corporations kind of cooperate today. You might want to ransomware some people, but you don't have the infrastructure for it. Well, guess what? Someone with a botnet does. So, someone with a botnet is going to be like, we have access to millions of computers. We can spread your malware. Just give us like 30% of your earnings. And there you go. There's the deal. Some of them even have like customer support. And damn, like it's better than most companies I've seen today. So we'll kind of go into that. I really like the customer support aspect. It's quite funny. So this is example number one. I'm not actually sure if this is real. I found it on Twitter. I found it hilarious. That's why it's here. But supposedly someone got ransomware. They say, oh, sorry, my monthly income is only $400. Do you really want to do this to me? And then the ransomware author responds like, no, actually we don't. We've overestimated the income of the population of your country. So you don't have to pay, we'll decrypt your files for you. But if you would like to, you can donate to this Bitcoin address at the bottom. This is great. So I don't actually know if this is real. I really hope it is, because this is fantastic. Now onto the more kind of serious side of things. This is a 100% real example. There's some malware authors that have worked together with different malware authors before, and now they have their own product. And damn, they have like even ethical principles. Like we want like attack medicinal industry. We want attack like the government. Education, like universities and schools, things like that. And at the bottom, they even give you like guarantees. We will guarantee decryption of one test file. We guarantee that we'll give you like decryptors. And this is the first thing you see when you get to their page, and you're like, wow, I wish companies in real life that were not illegal did that. Like this is like pretty professional, and they seem to really care about their business practices. Which is, even though it's illegal, they really care a lot, and that kind of puts into frame how big of a business this actually is. I think this is one of the best ones I have. So I think last year there was a ransomware called Ragnar Locker that infected a company called CWT. They had a very civil discussion. They were originally asked to pay $8 million. They managed to negotiate it down to $4.5 million. You could negotiate over customer support with ransomware authors. That's a thing. And they even got security tips. Like turn off your local passwords, opt your passwords every month, have at least 3 sysadmins. So as we can see, you wouldn't expect ransomware authors to go out of their way and give your company security tips. That seems kind of counterproductive. But these guys seem to care a lot, and it really paints the picture that there's so much money in this kind of illegal business that they've actually kind of formed it after the image of corporations and a bit how they work today. So they really kind of care about their business relations, so to say. So now, we might also ask ourselves, why would we analyze malware? I would say to convince yourself of how broken everything is. You think Windows is bad, it's worse than you expected. Curiosity, of course. Malware authors are very intelligent. Like the technology that they put forward, even though it's with malicious intent, is actually very interesting. They find a lot of quirks in computer systems that you might not have actually thought about. So people who reverse engineer malware are very interested in seeing what they do, and of course how we can prevent these things from being abused. I think another kind of big portion of all of this is that threat prevention and threat removal. That's a big thing because everyone wants an antivirus. No one wants to have malware on their computer. In order to develop an antivirus, you really need to reverse engineer malware and understand how to prevent it that way based off its functionality. The security of your company. Sometimes you might get a panic call at 3 a.m. of a company going like, we just got ransomware, please help. And that happens every single day. And that's why malware reverse engineers exist, because they got ransomware. You need to figure out exactly what the ransomware does. Is there any other functionality? Have they exfiltrated more data than we expected, right? So there's a lot of kind of security considerations in those kind of incidents, and that's why we analyze it. It's really about protecting companies, protecting ourselves, protecting others. That's a kind of a big deal. Because in the end, companies incur millions of dollars in loss, and they're not happy about it. Some companies don't even care about their security until they actually get ransomware, and it comes and bites them back in the ass. But hopefully they in the end kind of learn their lesson. So yeah, I mean, those are kind of the motivations for what malware is and why we look at it and why we care. So I guess to kind of delve into it further, I would like to talk a little bit about the Dridex banking Trojan. So this is a sample that I reverse engineered as part of my internship at F-Secure this summer. So what I would like to do is to kind of guide you through the process of what reverse engineering is, how it works, and then kind of look at some interesting quirks that I found in the malware that I reversed, and the kind of aspects that we can discover when we reverse engineer such a thing, and kind of explain the thought process behind of how I work. If you would like to ask questions, this is going to be sometimes, for some people this is quite a difficult topic. So if you have any questions, just raise your hand. I will try to, pick you out and answer it. And of course, there's always the questions at the end of the presentation that you can use for that. So before we kind of get into the malware, we need to understand how a CPU works. We need to be on the same page about how we understand this. So a CPU has things called registers. We can think of them as small boxes where you can put data. You can't put a lot of data in there, just tiny bits, like a number. And it has these storage units and it uses them a lot. So for a CPU to actually do something, we need to tell it to do something. And we do that by giving it instructions. So each CPU has a predefined set of instructions that it accepts, and we can give it to it. So for example, mov x, 5 tells the CPU to move the number 5 into the register x. And this is how software works. When you're executing software on a processor, it goes instruction by instruction, executing it, and basically doing exactly what you're telling it to do. Now, to kind of mention another aspect of all of this, it's main memory. Main memory, you can think of it as a bucket. You can put loads of data in there. You can retrieve data. So for example, you have a gigantic array of numbers. And the CPU is oh, I would like to do something with that array. So it goes into the bucket, takes that array out, does some operations on it, and then it puts it back in the bucket. And then, perhaps another part of the program can use it, or some other program can use it. So it's basically a bigger storage unit that we keep in mind as we go along. And every CPU has its own instructions, and we have billions and trillions of programming languages. So one might wonder, how exactly does the CPU understand what to do when we write Python, when we write C++, Golang, Ruby, Rust? There's lots of different languages out there, and I would kind of like to simplify this entire process a little bit and talk about native languages. So these are languages that go through the process of compilation, and I will tell you what that is. Basically, you write code, you put the code through a compiler, and it's basically translating a language to another. So you're kind of translating your code that you wrote into CPU instructions. And when you've done that, your CPU is happy, it knows what to do, and it does it. Now, as reverse engineers, we would like to go in the opposite direction. When someone gives us a malware sample, we don't have the source code. We wish we had that. That would be great, but that would kind of break the point of it. So we like to go from CPU instructions to code. We call this process decompilation. Unfortunately, it's incredibly difficult. It's not an easy thing to do. There are attempts at it. Sometimes they're good. Sometimes they're terribly bad, and you don't know what's going on. So you wonder how do we recover information from a compiled program where we only have the instructions? Well, let me tell you, we just read the instructions. That's one way of doing it. This process is called disassembly. So, when you have a file on disk, it contains data that represents these instructions. And we can put it into some sort of tooling that we call a disassembler, and then it gives us like a nice laid out, which instructions are executed in what sequences. And to a trained reverse engineer, this is a classic process of just reading the instructions, and from that you can gather what the program as a whole is actually doing. There's, of course, decompilation. There's tools that are either free, some which cost around $10,000, that do this thing for you. They're pretty good at it, not perfect, but there's software that attempts translating CPU instructions back into actual code. Usually it's in the syntax of C. And it's very useful because it speeds up the process. Reading instructions is tedious. Like, a line in C++ could be like 5, 6, 7 instructions in assembly. And reading that and understanding it, it takes a lot of effort. So having tools that kind of attempt at translating it backwards is quite nice. And of course, the kind of final aspect of recovering information is nothing else than actually running the program. So, we want to debug it. How does a ransomware work? Well, why don't we run it and then see what it does? So we can have a lot of different monitoring tools that, monitor any functions that it's calling, any APIs it's going through, or we can even, step through individual instructions at runtime to investigate like a real-life pattern in what's going on. So I guess the main kind of separation here is that disassembly and decompilation are processes that are static. You're not running anything. You're just putting in data and trying to understand what it does. Whereas debugging is a dynamic process. We run the ransomware or some other form of malware, and we see what execution paths it takes and what it does live on a system. And usually when we're reverse engineering, we're combining these two approaches. We do some static analysis and we do some dynamic analysis because quite often we can't just stick to one as things get kind of progressively difficult, as I'll explain a little bit later. Right, so now that you've kind of hopefully understood a little bit about what reverse engineering is and how it works, we can start talking about Dridex. So Dridex is a banking trojan. All it does is kind of steal your banking information and tries to execute fraudulent transactions on your behalf to steal your money. We see that a lot in Switzerland. A lot of the samples that I pulled, for example, they've been particularly directed at Switzerland because these are the things that this type of malware would be targeting, financial and banking institutions, and yeah. So we might also ask ourselves, like, how does this actually spread? Botnets. These people behind this malware have struck a deal with a couple botnets, and they're like, yeah, can you spread the malware for us? Can you, do some spam campaigns using emails and send people attachments that they shouldn't be clicking? And that's what it does. It uses botnets to kind of spam email attachments to a lot of different institutions. And effectively, someone goes, downloads that Word doc or that Excel document. And even though there's a big warning sign saying, do not click enable content unless you're like absolutely certain that this is safe, they go ahead and click it, and boom, there's your money gone. So don't do that. Don't click enable content on Excel sheets unless you're absolutely certain that it's safe. And I'm not targeted by these people. I hope none of you are either. So the next question would be, how do we acquire samples for such a thing? How, because we want to look into it, how it works, but we don't have the physical samples. Fortunately, the cybersecurity industry is quite nice to us. We have a lot of people that like to be cooperative, and we have malware sharing websites. So websites like VirusShare, VirusTotal, Malware Bazaar, which is one of my favorites. And people upload their samples. You can go and grab them, analyze them for yourself. It's free for all. Yep.
Can you then reshare them?
Yeah. Yeah, I mean, you could. I mean, like, if you re-uploaded it to the same system, it would detect the hash of the sample being the same. But you can upload them somewhere else or give them to your friends. I don't recommend doing that. But yeah, the thing with like Dridex is that servers for Dridex go down fast. You know, when it still steals these banking credentials, it has to send them somewhere. They have like command and control servers where all that information is being sent to. And when these samples are uploaded for the public to see, you know, these authors notice it. They're like, okay, that's a problem. So we're going to take our servers down. And, you know, this happens sometimes within 1 or 2 hours. So they're constantly monitoring their behavior and taking and changing the infrastructure as they go along, which makes my job a little bit difficult because, you know, I don't always have, 10 hours a day to keep watching samples in order to grab them in a reasonable time frame to start analyzing them. Fortunately, Malware Bazaar has monitoring tools, so you can sign up for like email notifications and wake up to something like this. You know, you love to see like 100 emails. I think Gmail actually separated it into like 5 different ones, so I had like 500. So I was like, well, that's a lot of samples. What do I do with those? You know, fortunately, some of them were quite recent. One of them I managed to catch within like 10 minutes. And what I do is I download it, I start executing it in a virtualized environment where it's safe, and I kind of start poking it a little bit here and there to see what it's actually doing. So after that process, I have kind of made a very nice chart for you here to describe what actually goes on after you click enable content in the Excel macro. So we see that, you know, you click the Excel macro, and what it does, it downloads another kind of file from somewhere. And would anyone like to guess where? It's actually, I think, something we all use every single day. Yeah? No. Good shout, though. I think they've used that before. Sorry? No, not Drive. So, a chatting application. Discord. Yeah, Discord. It's like, you know, I guess their thought process must have been like, oh, you know, paying for service, like, that's a lot of money. What if we just got, like, free infrastructure? You know? Just take Discord, you know, upload a file, copy the link, there you go. So problem solved, you know, nobody cares. So yeah, it downloads things from Discord, and it then runs it using something called rundl32.exe. I'm not going to delve too much into what that is, but effectively, you know, it runs the thing that it downloaded, and then the malware actually starts doing things on your computer. So malware is usually separated into multiple stages. You know, it starts with the downloading stage. It downloads something. You have it running, and then it decrypts itself like multiple times. In this case, twice. So, you know, you go through the process of, you know, you run it, it decrypts itself, then it does some funny stuff, then it decrypts itself again before it actually gets to the main payload where most of the malicious kind of behavior is hidden. And the reason it does that is because if you were to just download that file and put it in a disassembler and read the instructions, well, you won't know what's going on because it's all encrypted. And the only way to decrypt it is to actually run it or re-implement the entire algorithm, but I don't think that's a good idea. So the easiest way is to just run it and do something called dumping. Basically, when the malware is fully decrypted and running in your memory, you can take a snapshot of that memory, save it to disk, put it into your tooling, you know, your disassembler, debugger, whatever. You have all the instructions that you want that are actually performing malicious behavior. And you know, you would think that we're done here, but it's like, well, malware authors don't like us. They make things difficult. So even after you've decrypted things, they still make the process continuously difficult through various types of obfuscation and other tips and tricks that, you know, kind of quirks that they've kind of come up with to make the life of a reverse engineer a bit more miserable. Right. So I guess I would like to kind of show you an example of what the Excel sheet looks like. And it looks something like this. You know, quite harmless. There's just a bunch of weird numbers. And when you click that Enable Content button with the yellow bar, yeah, so what happens after that is that the macro runs. There's some sort of program running in Excel. It reads all of those numbers. It treats them as bytes. And it saves the file to disk before running it again. And the file that it saves to disk, that is represented by these numbers, is precisely this. So it's some sort of script that it's running. And they have implemented some sort of obfuscation, just gibberish that is unreadable. Fortunately for us, I managed to remove all of it using a simple regex query, so they didn't try too hard. But if you look kind of below the first blob, you can see all these links to discordapp.com. Don't worry, you can't download them, you can't infect your friends. They've been down since forever. But yeah, basically it downloads things, it runs them, and then we get into the kind of main meat of the malware itself. So before we kind of finish, I would kind of like to discuss a couple interesting bits that I found when reverse engineering this malware, and a couple things that they're doing to make the process of reverse engineering it a little bit more difficult. For example, API resolution. So, Windows has an API. People can use it to call functions. For example, get Windows directory A. What does that do? It just returns a string with the Windows directory. Simple as that. If you look at those functions in the disassembly, then they give a very good indicator of what kind of behavior is happening. Malware authors don't want that. So what they do is that they figure out those APIs at runtime. So when you look at them statically, you just see something like func and some parameter, and you're like, well, what does that do? Well, I don't know. So in order to figure that out at runtime, they resolve hashes. So they have a function that resolves hashes. Basically, it takes two parameters. The first one is the hash for the library that they're importing from, and the second one is the hash of the function that they would like to import from that library. And as this code runs, it finds that function at runtime, it puts it as a variable into func, and then that makes func callable, and it does something. Obviously, you don't know what it is until you run it. So there's kind of two ways of approaching such a problem, and each time the answer is really to have some good tooling. So one way of kind of going about this is, having a debugger that logs every time this function is called. And every time this function is called, we can kind of log what sort of API was returned to us. So that's one way of going about it. Another way is to kind of create a massive lookup table, which is what I did, and just take each and one of those parameters, look it up in the table, and just insert some comments here and there to describe what kind of functionality we're expecting. So, the kind of idea with this is obviously to make it harder for me to understand what the malware is actually doing, and this is why it requires like a combination of static and dynamic methods, because sometimes you won't be able to figure out what this does unless you actually physically run it on a computer. Right. So the next kind of interesting thing that they do is configuration. Obviously, the malware needs to know where to connect to. Like, it can't just send data to random IP addresses. So they need some sort of config stored somewhere. Fortunately for us, Dridex stores the config in the very same location in every single sample that I found. So what can we do? Well, we can make more tooling. We can use Python. Python is a great tool. It's a great language. It's very helpful when you're reverse engineering. I think I use it like every single day. But the gist of it is that, we take the file, we parse it using Python, we find the area where the configuration is, and we just parse it out. And we get something like this. I'm not sure if you can see it clearly, but at the bottom we got like, so I'm running my Python script, and it gives me all the IP addresses that the malware can connect to. Reverse engineering malware is not only about understanding how these bits of malware work and what they do and how to prevent them, but it's also a lot about kind of tool development and a lot about kind of automating tedious tasks that we don't really want to do, but we have to. And I think that kind of brings me into the point about some future work that me or someone else would like to do in terms of Dridex, like looking at breaking their command and control servers. It would be an interesting idea to take multiple samples, extract all these IPs, and see if any of these are vulnerable? Can we infiltrate any of their infrastructure? Can we like prevent their operations from happening? You know, it's a very big task, but it's still an interesting one. And obviously another one could be reverse engineering their communication protocol, because usually they re-implement their own. Yes?
Is it legal to try to break into a malware server?
See, so this is the thing with these kinds of operations. It kind of depends. You know, if you're working on the behalf of the government, they don't care. If you're working on the behalf of some company, you usually have some sort of permission to do that kind of thing. So it's a very gray area where you have to be careful with the law. But yeah, continuing on, reverse engineering communications. You know, maybe we can write an emulator and pretend to be the malware and see if we can extract some information using that. And of course, the big idea of automation. Creating tools that make it easier to extract malware, maybe quicker to dump it from memory. You know, all these things that people need that make our job easier, but are just not there. You know, big problems and very little time. And I think that kind of brings me towards the end of my talk. So I hope I have kind of given you an understanding of what malware is, why we care about malware, you know, why we analyze it, and a little bit about what reverse engineering is and how malware works actually in practice. Now, if you're curious about malware analysis or kind of reverse engineering in general, I have listed some resources here. I highly recommend the first book called Practical Malware Analysis. This is how I started my journey back in like 2014, 15. It's a very old book, however, it's still very relevant. I think the only things that have changed over the years is the tooling that people use. There's also practical reverse engineering and some GitHub links. So I'll try to post them afterwards for you to make it kind of easily accessible. And yeah, I guess that's it for me.
Sorry, so is the hash resolver something that malware developers write themselves, or is it normally kind of continuous between different pieces of malware?
So a lot of the hash resolvers that you see, they have a lot of overlap. Quite a lot of malware authors use CRC32 hashes. It's simple, it's fast. So there's a lot of code reuse. Usually when malware authors cooperate, you can notice that in certain parts of their modules, because it's a very modular program. These are like very big projects. And you can take, you know, you can probably find this stuff on GitHub even. It's probably public. So, you know, there's a lot of code reuse. Sometimes people are a little bit more original, but usually not.
So, that may say a question, but when you get a snapshot of the main memory, once you run that malware, like, how do you know where to begin in terms of like what exactly is happening, like what exact instruction is taking place, like how do you kind of orientate your mind to its start?
So do you mean like where do you start reversing it to understand what's going on?
Yeah.
Right. So programs on our computers usually have a very strict structure. It's very rigid. So you know, when you write C++, for example, you have a main function. That's where execution starts. So the way that these tools are developed for taking these memory snapshots, they preserve that structure. So when you put it in a disassembler, the disassembler is like, oh, the main function is here. This is where execution will start. And usually what I do is, you know, I go into the main function, see what's happening there, kind of reverse, kind of progressively as functions are being called. Another way of going about things is when you have dumped a piece of malware, you sometimes do know the APIs that they're using. So if you're looking for specific functionality, you will try to look for specific APIs. So the way that our tooling works is that it can tell us where these APIs are actually used, and kind of we can then go to the area of the code where it's used, and we can kind of investigate that general area. So it's a bit like, you know, sometimes it's a bit going by the book and just going through each individual function. Sometimes it's being a bit more creative, looking at API calls, perhaps looking at some strings that are being used here and there, and jumping into random points of the software and hopefully kind of building it into a whole.
So that kind of shifts the determine where the entry point is?
Usually if you're working with like a format like PE, then the entry point will be specified in the header. So the disassembler literally parses out the file header, and the entry point is just an address, and the disassembler is like, yep, there we go.
What is the problem with the weirdness malware that you've had to disassemble, as in like when you something so obscure that you never really thought about it, and it's had to start getting together?
I think the most obscure stuff that I've seen was they spent like a lot of time creating some sort of structure with like lots of pointers everywhere. It was like massive, really weird. And then they passed that structure around in every single function. And then they started, doing weird stuff to it. I don't exactly remember the specifics, but they just made, some simple function calls as complicated as possible. So it was very hard to wrap your head around like where the program was going to execute because of the way that they've kind of made it up.
When you mentioned about how the malware would call APIs from like Windows OS, etc. So does this imply that malware will have to be specially designed for different OSs, or do they kind of overlap in the API calls?
Yeah, so malware is usually designed for a specific operating system, because Windows can only run specific types of files, Mac can only run specific types of files, and the same goes for Linux. These are kind of platform dependent, and sometimes you can reuse code if you make it general enough, but most of the time these are targeted systems. Malware authors might investigate what type of system is someone's infrastructure running on. And they're like, okay, it's Windows Server. Well, we'll use malware that is targeted to Windows. If they're running Linux, then they might change their mind and do something else. But yeah, it's basically specifically for each platform quite often. Yep.
So you mentioned that when you're analyzing malware, you do it by running it in a virtualized environment. How do you know that the virtual environment is safe to be running malware in?
That's a really good question. The answer is you trust the engineers. So the way I view it is there are these virtualized environments are, they are quite secure. It's tested. It's a lot of work goes into it, and escaping from something like that is incredibly difficult. Usually, you wouldn't expect a malware author to drop a 0-day and escape a sandbox into malware that isn't, specifically targeted for some incredibly difficult and complex operation. Malware in general targets simple users. These types of things like sandbox escaping, you would probably not see that in the wild because it's just not worth it for the malware authors to spend such a precious bug that you might find like once in every 10 years on operations that don't matter as much. Obviously, if you're thinking like nation states, then that might be a different story, right? Because then they have much stronger kind of motivations for doing something. So it really boils down to how well engineered I believe that this software is that virtualizes this environment, and obviously also a bit of trust in the fact that the malware won't have any 0 days under its sleeve.
That electronics, like lower level stuff, will be more vulnerable compared to like nowadays, because like big companies, they will try to make their program secure, but like lower level stuff, they sometimes do some hacky stuff like in the program. So will they be more vulnerable?
Yeah, so I think a lot of the vulnerabilities tend to be on the side of software. There is malware that tries to attack very low level stuff, things like bootkits. They try to infect the boot process, so before you even boot into your computer, it's already running, it's doing things. In terms of hardware, I think a lot of companies have implemented very interesting security measures in terms of like a verification process to verify that when your operating system is booting, for example, that nothing weird is happening. And with new standards kind of coming about, it's increasingly difficult. And also, targeting hardware is a very difficult task because everyone has different hardware. So typically, I would say targeting hardware would be more in very niche scenarios. Like with the case of Stuxnet, they actually targeted programmable logic controllers and kind of fried them to the point where they just didn't work. But you don't really see that in the wild because it's such a high effort thing to do, and it's obviously very difficult to target millions of users who are all running different things.
With the kernel inspector is made about years ago, and with people, especially gamers, disabling these spectrum applications. Have you noticed that a lot of malware has tried to, because for a lot of malware forms I've read, there's a lot was if there wasn't really any malware trying to take advantage of the spectrum. Did you notice that when you reverse engineering?
I've not encountered malware that has actually tried to abuse it. This would be the type of malware that tries to sit in the kernel, so the low-level part of the operating system. Usually the malware that I encounter is quite high-level. It does stay in kind of user mode and doesn't touch the kind of small components of the operating system. I'm sure that there are malware authors who have tried to abuse it or tried to look for similar bugs, but not that I've encountered myself.
You mentioned 0 days. Do you think like malware authors target like the 0 days, like newer 0 days and like newer systems, or older 0 days for like systems that are vulnerable? For example, like in the chat, they have like older systems that are infected.
I think they target both, but they usually tend to do some sort of investigation sometimes into like, oh, what kind of infrastructure might this company be running? And I think targeting older technologies is a pretty prevalent tactic because people don't update their computers. You sometimes see like a Windows XP screen on a train. That's a thing. So the fact that you can quite reasonably conclude that people will not necessarily update their software in time, betting on older exploits is actually quite a good idea. Obviously, with newer systems, I think they do that as well. It's just a bit more complicated because you have to discover those bugs. And in the moment, it might not be worth it to actually use that bug unless you're performing something that you find incredibly important.
It would be like better to get a bug bounty instead of
I mean, it depends, right? Like, if you're a ransomware author and you're like absolutely certain you're going to make millions of this, then you're probably going to burn that bug there. But yeah. So, did you have a question?
You mentioned something about investigating command servers and stuff like that as a kind of game we could do, but there's so much money involved. Maybe you need a health warning because if you know where they are, they can probably figure out where you are.
Yeah, that's true. I mean, these operations are usually conducted, I think, in very strictly managed environments, right, where people are very, very certain about their security and take ridiculous precautions almost to make sure that you're not found out. So I'm guessing, like, if you're working at, say, like a government level where you would be trying to attack such infrastructure, I would at least hope that they have methods for maintaining a certain level of anonymity. Any more questions? Yep.
With languages like Go becoming more prevalent, have you recently discovered more obscure languages kind of popping up for malware to be written in? And does that pose new issues to reversing it?
Yeah, that's actually a pretty good question. Golang, so actually, I don't think I've seen much more than Golang being used in the wild, at least. But Golang is growing. Golang is really easy to code in, and it's terrible to reverse engineer. You look at it once and you're like, nope. No, we don't like that. And I think that's what malware authors like with Golang. It's ridiculously easy to use. And when a reverse engineer looks at it, he's just like, you're going to spend significant amounts of time trying to figure out how Golang works internally before you actually figure out how the malware works. And that's why they use it. So Golang is like exponentially increasing in the use of malware. I don't actually know about any other languages, but potentially. I would love to see a Haskell malware. That would be funny. Right. Are there any more questions? If not, then I think we're done.